Hi, I am Naga Vempati. My final project is credit card fraud detection using AutoEncoder and ANN. Here I am going to explain my project and give a short demo. Fraud detection is one of the business problems faced by commerce companies. Fraud Benchmark Report 2017 by CyberSource states that 79% of the North American businesses conduct manual reviews to detect fraud transactions. So the manual reviews are still prevalent. It also states the importance of automated screening for efficient fraud detection. There are solutions that use machine learning techniques to detect fraud transactions. In this project, I have tried to use deep learning to provide an automated solution for this problem. I have created a classification model using AutoEncoder and ANN. The data I have used is from the Kaggle website that is shown here. Before going into the solution, let's explore the dataset first. The dataset contains transactions occurred in 2 days in September 2013 by European card holders. There are 28 PCA transform variables. The input variables were PCA transformed for confidentiality reasons. The other variables are time, amount, and class. Time represents the seconds elapsed between each transaction and the very first transaction in the dataset. Amount is the transaction amount. Class has 1 for fraud transactions and 0 for not fraud or normal transaction. All the data types are numeric. First, let's see the transaction class distribution. That is, how many records we have for normal class and how many for fraud class. Seeing the graph, we see that there are very less number of fraud records compared to normal ones. This shows there is high data imbalance in the data set. Now let's see the relationship between time and class. This graph here shows the time when the transactions occurred for each class. And you can see that for each class, the transactions are distributed all over the timeline. You don't see a particular transactions grouped at one point of time. This shows that there is no relationship between time and class. So I have decided to drop the time column while training the model. As we have seen before, the main challenge with the dataset is that the data is highly imbalanced. We have 0.17% of fraud transactions compared to normal ones. So in case we have a random model that predicts every transaction to be normal, then we would have 99% accuracy. But that would not be an efficient model. So I have used synthetic minority oversampling technique to oversample the data in order to generate a better balanced data set. This algorithm intelligently oversamples the minority class by creating synthetic examples rather than oversampling the data by replacement. Here the minority class is the fraud class. So the algorithm works like this. For every minority class sample, the algorithm takes the difference between the sample and its nearest neighbor. Then it multiplies this difference by a random number between 0 and 1. Now the product is then added to the original sample. In this way, we get a random point along the direction of these two features. So this is how it creates examples. Now in this project, the minority class was oversampled at 500% of the original data size. Coming to the model, the first block of the model is AutoEncoder. AutoEncoder, as we all learned, is an artificial neural network that can be used to learn patterns in the input. In this project, AutoEncoder was used to do unsupervised learning. It takes transactions as input and tries to learn the patterns in the transactions. These patterns are further used for classification. The autoencoder that I have used in the model has 5 hidden layers. The first layer takes the inputs and then it has 3 encoding layers and 2 decoding layers. These layers try to learn the patterns in the input and reconstruct the input. The next block of the model is a neural network. It takes output from the deepest hidden layer of autoencoder as input. It has two layers, one dense layer that takes the input and an output layer with sigmoid activation that classifies the output. Coming to the results of the model. I have achieved around 82% accuracy with AutoEncoder, and the accuracy of neural network was 99%. As we have seen before, accuracy alone is not enough to determine the quality of the model. So I have also used AUC curve. The AUC curve shows the ability of the model to correctly classify the input to be normal one or a fraud transaction. So the AUC measure was 0.868 for this model, which is a good one. Here we see the confusion matrix that I have created for the predictions by the model. The y-axis is the true label, that is the actual y values. And the x-axis is the predicted labels, that is the predicted y values by the model. So all the horizontal rows represent the predicted labels and the vertical columns represent actual labels. So the model has predicted 57,021 transactions as normal that are actually normal. And it also predicted 129 transactions that are fraud as normal. In the similar way, the model has classified 56,475 transactions as fraud that are actually fraud and 162 transactions as fraud that are actually normal. So the true positive rate, here I'm considering classification as fraud a positive case, is 99%. That is actual transactions that are classified as fraud. And the specificity or the true negative rate is also 99%. These calculations are done on the oversampled data. Let's see how the model performs on the original data. Using the model, we predict on the original imbalanced datasets. Looking at the confusion matrix, we can say that of all transactions that are marked normal by the model, 9 transactions are actually fraud. And of all transactions that are classified as fraud by the model, 779 transactions are actually normal. That is, the sensitivity of the model on the original dataset is less. It's around 38%, which is very less compared to 99% on the oversampled data. So this is where more research can be done on creating better models so that we have better sensitivity. Now let's see the demo. So this is the Jupyter notebook in which I've written the code and ran it. So first you see all the libraries that I've imported. The main libraries are INB-Learn, which has all the sampling algorithms, and Pandas for data wrangling, Matplotlib, sklearn, stat models. These are for drawing beautiful graphs, plots, and I've used Keras with TensorFlow to build the model and train it. So first we are reading the data here as a Panda data frame. And then if you see the data, it has 28 PCA transformed variables with amount, class, and time as other columns. So we see the size of the data set. It has 284,807 rows with 31 columns, and there are no null values. So as we move on to data exploration, we see that the data is highly imbalanced. So when we use value counts function to count the different to count the number of records for each class, we see that the normal class has 284,315 records and the fraud class has 492 records. So if you see the bar plot here, it is more apparent. The normal transactions, the height of the bar is so high, and the fraud transactions is just like a line. So then we see the relationship between time versus class. Here I plotted a scatter plot between time and class, and all the red dots that you see here are for fraud transactions, and all the blue dots that you see here are normal transactions. So the transactions are distributed throughout the timeline, so there's no evidence of relationship here. And I've also tried to see the distribution of amount among the two different classes. One interesting thing I've found here is that the mean amount for normal transactions is 88, whereas the mean amount for fraud transactions is 122. That is, though there are so many normal transactions compared to fraud, the mean is actually higher, which I found really interesting. So I've used a pyplot function to plot the distributions of the amount among different class. Now coming to oversampling. So first I dropped the time column. Then I've separated the data set into labels and features. The class column is the labels. Now I've created a smooth object here so that we can call fit sample function on it by passing the labels and features. Here I've used all the default features. So the default feature is auto here, which is after it's sampled, we will have 1:1 ratio of majority and minority classes. So there is no majority and minority anymore. So you see, after the sampling, we have equal number of fraud and normal transactions, and the bars are of equal heights now. So the data looks more balanced now. The next is building the autoencoder. So first I've split the data into three sets. First set is used for unsupervised learning, second set for supervised learning, and the last set is the test data. So first I have split the data into 80-20 ratio, train and test, and this train data I have split into 50-50. Now I've used model checkpoint to save the best model. So it has mode max and monitor as validation accuracy. So it monitors for validation accuracy. Whenever it sees that a better validation accuracy is achieved, it saves that model as the best model. Now the input is shape 29, and then we have 5 hidden layers with 15, 8, 4, 8 and 15 nodes. So the idea I have used here is that if the input has shape n, and then the next layer has a shape almost n by 2. Here 29 by 2 is very close to 15, so I've used 15, and then 15 by 2 is 8, I mean close to 8, and 8 by 2 is 4. So I've tried different architectures here. I've tried with 3 layers with 10 neurons, 5 neurons and 10 neurons again, and I've also tried with 4 hidden layers, but this one with 5 hidden layers gave me best results. Then I've used RMS prop optimizer here. Again, I've tried different optimizers: RMS prop, Adam optimizer, ADA delta, gradient descent, and I found RMS prop to give optimal results with learning rate 0.001. While tuning the model, again I've tried different learning rates: 0.1, 0.01, 0.001, 0.0001, and 0.001 gave me best results. So I've used that for my final model. And my loss is a root mean squared error. Since all the columns are numeric, I found mean square error to be best loss. And here you see RMS prop optimizer, and I'm capturing mean square error and accuracy metrics, and I'm training the model for 50 epochs. That is, it runs for 50 times the same thing. and batch size is 30. So the whole data is trained in 30 batches, and this is repeated for 50 times. So while training this, I got a best accuracy of 82%. If you see here in the output, if I scroll up, you see here it is saving when the accuracy moved to 82%. Then we load this autoencoder model, and when we see the summary, it has one input layer with 5 hidden layers and then the output layer that reconstructs the input. Now we create another model that has first layer as the input layer and the last layer as the fifth hidden layer. So when we print this model summary, we see that the first layer is input layer and the last layer is the dense layer, that is the deepest hidden layer. So that we can use this class model while doing the classification as a first part of the classification model. So then using the autoencoder model, we do our predictions and we capture the loss, that's MSC, and also what's the actuals, that is white test, and we draw a ROC curve. C gives a measure of the area under this curve, which determines the ability of the model to classify an input into a normal or fraud transaction. The AUC measure here is 0.868, which is pretty good. Then coming to classification model, we see that the first we have added the class model that we have built before, the autoencoder, and then it has a dense layer with 256 neurons, and then one output layer with sigmoid activation, which classifies input into normal or fraud, which gives 0 or 1 as output. Now, as same as before, we use model checkpoint to save the best model, and RMS prop, and loss as mean square error. And again, I'm capturing mean square error and accuracy here, and I have run this again for 50 times, passing 30 batch. So here I could achieve an accuracy of 99%. Now let's see the predictions. So I load the model and I predict on the test data. So since this is a classification model, you get any value between 0 to 1. So any value higher or 0.5 that I have coded as 1, and lower than 0.5 as 0. So that's how I have coded here. And when we draw a mosaic plot between the predicted and the actual, we see something like this. That is, this much of the data that is 0 is predicted as 0, and very little of the data that you see here as a one line, that is 0 is predicted as 1. So the same thing here. So much of the area is predicted as 1, that is 1, and very little of the area, that is 0 is predicted as 1. And the same thing we see here in confusion matrix. So if we plot the confusion matrix, you see that of all normal transactions, that's actual normal transactions, here 57,021 are predicted as normal and 162 are that is normal are predicted as fraud. So similarly 129 that is fraud are predicted as normal, and the rest 56,475 that are fraud are predicted as fraud. In conclusion, I have built a model using autoencoder and ANN to classify the credit card data set into fraud and normal transactions. And we could do better in terms of sensitivity. So we can do more different experiments using different sampling algorithms to see if that helps. Or we can even try different unsupervised like RBM models to see if that gives a better result.